Let's look at another trig sub example where it's going to be a little more complicated. I've made sure the numbers work out nicely, as with lots of book problems, but it introduces a little bit more algebraic complexity at the start. So here's the problem. We've got a graph of a funky looking function, y equals the square root of a somewhat complicated quadratic. Here's the graph of that function, and it's enclosed by the x-axis, x equals 5, which would be a vertical line right in the middle, and x equals 16/3, which is about 5 1/3, which is like right around here. So it's going to be a little strip of this, of the area under that curve. So very standard, not trying to make that part super complicated, just going to be the integral from 5 to 16/3 of that function dx. But, and so, well, if you look at just the type of it, what kind of technique you would expect to use, it is the square root of a quadratic, and so we would expect trig sub to be a good way to do that. But we need to complete the square on the inside, because we need to see this as just a constant squared plus or minus something with x squared. And this linear term, as so often happens with quadratic, just totally screws us up if we can't get rid of it. But we can, and that's what completing the square is for. So, brief tour of completing the square, the way I like to do it. The key is that this is the problem, the fact that there's two x's, and in particular that x to a linear power. The constant is not a problem. We're going to kind of leave that out. But a minor complicating factor, but significant, is the coefficient in front of the x squared. So what we're going to do is we're going to factor out that from that x squared, and we need to keep the x really close to the x squared so that we can get them to interact and get that x to go away. So we need to factor out the minus 9 out of that as well, and then that becomes a minus 10x, and then minus the 221. Okay, so now a lot of folks teach completing the square. You have to like add stuff to both sides and things like that. I don't think it's a good idea. It actually happens, the key steps happen entirely inside these parentheses. So I'm going to write that as x minus 5 quantity squared and hope that that's exactly right. And we'll discover it's not quite right, but we can fix it easily. Let's just do a little sidebar computation. Why did I do minus 5? It's because a squared plus 2ab plus b squared, the perfect square trinomial formula. X squared minus 2 times x times minus 5 gives me a minus 10x. So far I've got a perfect match, and that's the important part. But it also gives me a plus 25 that I do not want. Okay, so that's easy to fix though. What I really have is that minus 25, so I just have to subtract it off. So I like thinking of it as this matches everything I care about and gives me something extra I don't want, and then I just subtract off the constant to fix it. So what's really going inside here is the minus 25. Okay, the whole thing with the minus 25. All right, and then there's still a minus 221. Don't delete it, but we just don't do anything complicated with it. So now it's just cleanup after this. We just want to combine the constants. Minus 9 times minus 25 is a constant, and the minus 221 is a constant. So we're just going to redistribute the minus 9, the one that we factored out a minute ago. So it's going to be plus 225 minus 221. And yes, I did contrive it a little bit so the numbers aren't too bad. That ends up being just a plus 4. Okay, if you're wondering why these weird numbers at the start. So it's not too bad. Okay, so we can rewrite this now. Okay, as this nice quadratic. Okay, and you know I'm going to rewrite it with the 4 in front because it's leading negatives are a little weird and they look more elegant if you don't lead with them. Okay, so now it's closer to what we see in other U sub problems. It's square root of a constant minus something that's roughly like x squared. Okay, so let's do a U sub to get it even more like that. So we're not doing the trig sub quite yet. You can do all this in one fell swoop once you get used to it, but it's a pretty good idea to not have to. So there's two choices. We could just do u equals not x minus 5 here. That would be smart. It would be fine. Or we could do, we could write this as 3 squared times x minus 5 squared and make u equals 3 times x minus 5. I think what I'll do is I'll do the least sophisticated, sort of least ambitious substitution to not assume that you're looking ahead too much. Just u equals x minus 5. That's it. Du is going to be dx. That's a nice thing, just really easy. And we got to change the limits. Remember to do that. If x equals 5, in fact, in this case, it actually makes it nicer. U equals 0. Woo, that's nice. And if x equals 16/3, well, that's 5 plus 1/3. And you subtract 5 off, you just get 1/3. Okay, so this is nice. Let me just, oops, copy this. It keeps thinking I'm right-clicking. This new computer is sort of annoying. Okay, I'm going to copy this down, maybe like way down here. Okay, and so in terms of that new variable u, it's just going to be integral from 0 to 1/3 root 4 minus 9u squared. So it's still a little complicated in there, but it's definitely back to what should be home base once you've done a few trig sub examples. All right, so now type. We need to know the type. It is constant minus a square. So we got a minus here, and we got a positive constant minus a square of the variable, and that's going to be a sine substitution. So it's good to be familiar with it enough or have a reference that tells you it's a sine substitution. So the key identity that we're going to use is that 1 minus sine squared equals cosine squared. And we probably want to just be really careful, especially since we have a definite integral here. We want to make sure that we use the right kinds of thetas, the right values for theta. This is going to be nice as long as we're in kind of the standard bounds for theta. Oops. Yeah, pi over 2. Okay. And so we're going to want to check that when we do change the limits to thetas that we're not going outside those bounds. It usually isn't a problem for sine and tangent substitutions. If you do the secant substitution, it can be really tricky. Okay, so what do I need to match? I need to match 4 minus 9u squared with something involving a 1 minus. Well, I can't just change the 4 to a 1, but I do the same thing I do in pretty much every other example. I factor that out. Okay, do the algebra carefully. Okay. And I'm just going to write that as 1 minus, and I'm going to write it as something squared. So almost always if this is not a 1 to begin with, factor that out, see what happens, and then write it as, what's squared here as one thing, quantity squared. Yeah, I forgot the square. Okay, that tells us the match. The key thing is that 3 over 2u has to equal sine theta for this to match, because we want this to equal 1 minus sine squared, which will turn it into cosine squared, allow us to square root it easily, etc. But while we're at it, let's do a little algebra in the sidebar here. That's going to be 2/3 sine theta. And so du, we're always going to want that. I always encourage people to do it right away. d theta. Woo, did something weird there. Okay, so we're getting there. Let's make sure this does actually work out. Double check it. If 3/2 u is sine theta, that's going to be 4 times the quantity 1 minus sine squared theta, or 4 cosine squared theta. Okay, and what did we actually have? The whole point to this is that it was appearing inside a square root. That's what made it necessary to do this. Let me just get right in here since it's kind of following that train of thought. That's the square root of 4 cosine squared theta. Now that's where we have to be a little careful. You shouldn't just blithely square root squares and say it's the same thing as just, say it just cancels out. But because we're going to make sure that we pick thetas in this interval, that's where cosine is guaranteed to be positive. If we didn't have that guarantee, or at least non-negative, whoops. If we didn't have that guarantee, we would have to put an absolute value here, maybe split it up into pieces to a lot of annoying stuff that has to do with absolute values. But we're okay, because we're going to choose the thetas in here. We're going to make sure as soon as we do the very next step and do the translation of the limits, we're going to be good. Okay, so we know how to translate the integrand. We know how to translate the du, the differential. Let's go ahead and figure out the bounds. If u equals 0, well, what's the simplest value of theta, in particular the value of theta in this region, this interval, corresponding to u equals 0? Well, that's theta equals 0. That's nice. Okay, and again, I sort of contrived it to make these nice. U equals, what is our other limit? It's 1/3. U equals 1/3 is going to be where sine, come on, sine theta equals 3/2 times a third is a half. Aha, that's a known quantity as well. Value of theta in here such that sine theta is 1/2. That's nice. And that's theta equals pi over 6. Okay, so now we're finally ready to translate everything. I'll put it all together. Okay, so there's ooh, what did I do? Oh my goodness, I didn't change this guy. Now I could get away with that here, because with that substitution, remember du equals equal to dx, but usually it's quite a terrible mistake. Okay, I just should have written a du there. So I'm glad I caught it, but it actually doesn't change it numerically. Hopefully you caught it already. Okay, so let's just rewrite what we had before, and then change everything carefully. Okay, so that's going to be integral from 0 to pi over 6. And then that square root was a 2 cosine theta. And then du was 2/3 cosine theta. D theta. Okay. And so just take the constants out and then see what kind of trig integral we get. Very common here to get a squared trig function, cosine squared theta. And that's where you'd be stuck if we didn't know that wonderful little angle or power reduction identity, which is that's 1/2 times 1 plus cosine 2 theta. It's plus for cosine, and it would be minus if we had a sine 2 theta. Okay. Okay, so that's going to be 2/3. Same integral without the 1/2. Let me just do it right down real quick. Okay, and now that's not too hard to integrate. 2/3 times theta plus 1/2 sine 2 theta from 0 to pi over 6. That's 2/3 times pi over 6 plus 1/2, and then sine of pi over 3 is root 3 over 2. Alrighty, and all of that, and then minus what you get at 0, but that's 0. Theta equals 0, and sine of 2 times 0 is 0. So that's the whole thing. And we could clean up. Let me just copy it one more time. We're pretty much done. We could just clean it up if we want to, and just take out a common denominator. I guess we could cancel the 2's, and then it's just going to be, well, actually, let me just not put it over common denominator. Doing funky stuff here. 5 over 9 plus root 3 over 6. And we're done.